We're going to begin talking about density curves, and most specifically we're going to be talking about the normal curve and the normal distribution. So let's begin with filling in the blanks on this. A density curve is an idealized mathematical model for a distribution of data. It describes the overall pattern of a distribution. The density curve for a data set might be exactly symmetric, even though the actual data is only approximately symmetric. So if we were going to sort of trace this figure, our curve looks pretty normal, but you can see that there are places in this where the curve is over approximating or under approximating, depending on how the bars fall on the curve. And so even though the curve looks normal, the data itself isn't perfectly normal. And in fact, very seldom do we see data that's perfectly normal unless we're looking at binomial situations. So a density curve has some basic rules. A density curve is a curve that serves as a model for the population distribution of a continuous variable. It's always on or above the horizontal axis, or x-axis. It has an area of exactly 1 underneath it. And that's because if I asked you, say, what is the probability that x is less than 30? Then I would be finding the area from 30 all the way below the area under the curve. So all of the possible sample spaces under the curve, and we know from the last section that if we're looking at every possible sample space situation, then we know that those probabilities add up to 1, and so the area under the curve is 1. A density curve describes the overall pattern of a distribution. The areas under the curve represent the proportion of observations that fall in a particular range. It is also an approximation that's easy to use and often accurate enough for practical use. Okay. Alright, so what are the disadvantages of using a normal curve or a density curve? In the situation you were looking at, one of the bad sides or downsides is if we don't actually have the data, we're just looking at the curve, then we can't describe what the outliers are. We can estimate where the outliers might be, but we don't have the exact data to talk about those outliers. Alright, and we've talked about this before, the relationship among shape, mean, and median. But on a right-skewed distribution, we know that the mean is somewhere to the right because it goes towards the outliers of the median. And the median breaks the curve into equal areas. So there should be 50% of the area on this side of the median and 50% on this side of the median. And of course my picture's not perfect, but it at least gives you an idea of how the mean compares to the median. In a symmetric distribution, we expect the median to be equal to the mean. And in a left-skewed distribution, we would expect the mean to go towards the left. It's skewed towards those, it's actually drawn or non-resistant to the outliers, but the median is still going to break the curve into half the area being on the left and half on the right. Okay? So you need to know those relationships. That's not going away anytime soon. All right, let's look at the next page. Some of the notation that I wanted to cover is, we've already talked about a little bit of it, but actual data comes from a sample of a population. And we know that, and we call whatever facts that we find out from that sample, we call statistics. And so if we found the mean from that data set, then we would call that a statistic. It's a type of statistic. If we talked about the standard deviation, then we talk about it as a statistic. And so the standard deviation is written as S, and then the calculator is written as S subscript X, and the mean is written as X bar. And then if we were actually talking about the population, or let's say you did a census and you were actually looking at the values from the population, but a lot of times it's what our ideal population looks like, then we talk about the mean as being mu and the standard deviation as being sigma. And this is the guy that came up with the normal distribution curve, the Gaussian distribution. He's on the Dutch-marked bill, so anyway, he's a smart guy. All right, let's look at the normal distributions. So we talked about density curves. Now, I'm going to kind of give you an example over here of another type of density curve where we could find areas, because it's not in your notes, but it is in your homework, so I wanted to just talk about it for a second. This curve right here is a density curve because it meets all our rules. It has an area of 1 underneath the curve. It's above the horizontal axis, okay, and it's continuous data. And so if I asked you to find the area, so find the probability that x is less than 0.7. Now it doesn't matter if I say less than or equal to on a continuous curve. Those are the same thing. So if this is 0.7 and I want to find everything less than 0.7, what I'm really asking you for is the area to the left of 0.7. And so if I look at this shaded region, if I want to find the area of that, I'm really just finding the area of a rectangle. So it's just 0.7, the length times the width. So it's just 0.7 times 1. And 0.7 times 1 is just 0.7. Now I could also do that with a with a triangular shape, all types of shapes, as long as the area underneath the curve is 1. The one that we use the most often, however, is the normal distribution, and what makes it different is that it's bell-shaped. So even though this one's symmetric, just like the normal one's symmetric, this one has a unimodal peak, one peak, and it's bell-shaped. All normal distributions have the same overall shape, but some are wider and some are narrow. So for instance, I could draw this curve like this. Well, we're going to pretend that looks normal. And it's just taller, but it's still a normal shape. What would control that? What makes this curve more compact and the other one more spread out? And the answer to that is the standard deviation. Okay, so the standard deviation is what controls that. So the exact density curve for a particular normal distribution is specified by its mean mu and its standard deviation sigma. These two quantities completely determine the shape of a normal curve. And they talk about in the book being able to draw the normal curve using inflection points. So let me just see if I can help you understand that. When I look at this curve, it's concave up and then it switches to concave down. That point at which it switches is called an inflection point. And for those of you who've had calculus, that's what it's called in calculus, the point at which you go from concavity up to concavity down or vice versa. And on this side, it's symmetric, so it should happen at the same place. And at that point right there, we're at about 2 standard deviations from the mean. And then right in the middle, of course, is the mean. And then between the mean and 2 standard deviations is about 1 standard deviation above and below the mean. And then the piece where it starts kind of, see how steep the slope is of this piece right here? As that's changing, that's about where we have 3 standard deviations. Okay, so that's how we break up and label a normal curve. All right, why don't you go ahead and turn to the next page. So we're going to talk about the empirical rule, and we're going to learn other ways to do the empirical rule, but it's called the 68-95-99.7 rule because it's an approximation of the area underneath the curve. And so on this curve, here's our mu, here's 1 standard deviation, 2 standard deviations, 3 standard deviations, and then 1 standard deviation below the mean, 2 standard deviation below the means, and 3 standard deviation below the mean. And on our curve, we estimate, based on the empirical rule, that 68% of the observations will fall within 1 standard deviation of the mean, and that 95% of them will fall within 2 standard deviations of the mean, and that 99.7% will fall within 3 standard deviations of the mean. So 68% of the data is falling within 1 standard deviation, 95% is falling within 2, and 99.7% is falling within 3 standard deviations from the mean. And so if you think about it, it's unusual to even be more than 2 standard deviations away from the mean, because only 5% of the population is outside of the 2 standard deviations. And it's really rare to be outside of 3 standard deviations on a normal curve. Okay? So as I look at this, I say, okay, well, what does that mean? Well, what that means is that since this is 68% of my data, then 34% would be in each piece of this. 34% above the mean and 34% below the mean. And if that's true, then if I look at this 95 and I divide it by 2, then when I divide 95 by 2, I get 47.5. So there's 47.5% on each side of the mean here, left and right. And if that's true and I subtract 34 from that, then that gives me 13.5% that's in this region. And of course these are symmetric, so that's true over here also. And then this is 99.7, and if I divide it by 2, that's 49.85%. And if I take this 49.85% and I subtract the 47.5% that I already had, that would leave me with 2.35% for this region. And of course it's the same over here, 2.35%. And now I know that I have 0.3% outside of the 3 standard deviations, because that's what's left. We know the area under the curve is 100% or 1. And so if that's true, if I've got 0.3 left, then 0.15% is in the tail region. And this allows me to talk about percentiles, because I know that the mu, the median, and the mean both are at the 50th percentile, because there's 50% that fall below it. And I can talk about percentiles at each of these marks now that I know the percentages, or what portion of the data falls within those standard deviations. So we talk about percentiles, and remember again that percentile is a proportion of observations that are lower than or equal to a particular value. And the notation that you'll see a lot of times is this n, sigma, mu, and sigma. And the mu is just the mean of the population. Remember again, sigma is just a standard deviation. So when they write this out like this, and let's look at this next one. They tell you you've got a normal curve with a mean of 25 and a standard deviation of 12. So I might just show you this and say, draw the normal distribution, or draw this distribution. And so then what you would do is you would come down here and you would draw your curve, probably better than I do because mine looks a little skewed, but we're going to go with it. And the point at which it changes concavity, remember, is about 2 standard deviations. So I'm going to label my curve first. And then 1 standard deviation was kind of right between there. And then 3 standard deviations is about right here. And so I've got my curve labeled with the mu and the standard deviations. Now what I'm going to do is put the numbers in. So I know the mean is 25, and I know that 12 is 1 standard deviation. So 1 standard deviation above the mean would be 25 plus 12, which is 37. Oops, sorry, 37. And then if I'm 2 standard deviations above the mean, that means I'm 2 sets of 12 above 25, or 24 plus 25, which is 49. And if I'm 3, I just add another 12, and that gives me 61. And then also going below, if I say 25 minus 12, that puts me at 13. Minus 12 is 1, minus 12 is negative 11. And now I've labeled this distribution. So when I ask you to label the distribution, then you need to make sure you show me the mu and the sigmas, and that you show me the values at each of those. Okay, let's look at some problems. Alright, so now we're going to do an example where we're going to use the empirical rule. And I just will warn you that once we do 2.2, you'll have a more exact way of finding those values. And so once we've learned that, that's what we'll use, unless it specifically asks us to do the empirical rule. The empirical rule is nice because it gives us a basis to think about things without actually having to calculate them too much. But we're actually going to use that now to answer these questions. So I'm going to draw this in. I'm about 1 standard deviation. Let's see, 2 standard deviations is where the concavity changes, so I'm going to draw that in. In my normal curves, you'll notice I'm not an artist, so this is challenging for me, so y'all bear with me. When I say I'm not an artist, I mean I can't even draw a straight line. Alright, so here we go. We've got all of our labels here. Now we're going to actually look at the mean and standard deviation in relation to this. So that's how we might write it, as 64.5 in 64.5, 2.5. The 64.5, of course, goes here. If I add 2.5, then that would give me 67. And if I add 2.5 to that, I get 69.5. And if I add to that, I get 72. And then if I subtract 2.5, I get 62. And if I subtract that, I get 59.5. And I subtract another 2.5, I get 57. So now I've got it labeled, but I'm going to go ahead and put those percents in that we did earlier. We know that within 1 standard deviation is 68%. So if you recall, that means there's 34% in each of these. Okay? And if you'll recall, there was 95% within 2 standard deviations. And so, since that was true, then if you took 95 and you took half of that, it was 47.5%. So if we subtract 34 from that, we had 13.5%. And since these are symmetric, that was on both sides. And then, if you'll recall, 3 standard deviations was 99.7%, and so half of that is 49.85, and if we take 49.85 and subtract these out, we got 2.35%. And then, of course, there was 0.3 left, so that was 0.15% in each of the tails. And so now that I have this, I can answer these questions. So it says, if a young woman aged 18 to 24 is 67 inches tall, what percentile does that put her at? So 67 inches tall is right here at the first standard deviation. Now, we know that below the mean is 50% of our data. So if that's 50% and this is 34%, then that means there's 84% below 67, so that makes 67 in the 84th percentile. Okay. Then it says, what percent of young women aged 18 to 24 are between 59.5 inches and 72 inches in height? So we're at 59.5 and 72. Now what I want you to notice is that 59.5 is 2 standard deviations below the mean, and remember, 2 standard deviations is within 2 standard deviations was 95%, and half of that was 47.5%. And then 72 happens to be 3 standard deviations above the mean, and so half of the 99.7 was 49.85. And so we could just add that 47.5% to the 49.85%, and that would give us 97.35%. Now that's not the only way to do it. We could just add these little values up. We could have said 13.5 plus 34 plus 34 plus 13.5 plus 2.35, and just added that area, all of that area together, and it would give us the same thing. And then the last one on this one says, what percent of young women aged 18 to 24 are between 57 inches and 62 inches in height? So now we're going from 57 to 62. So this area right here. Well, that's just 2.35 and 13.5. So we add 2.35% plus 13.5%, and that gives us 15.85%. Okay? All right, so you might want to try the next one on your own and turn off or pause this video. Try the next one on your own and then come back and see if you've done it correctly. So let's do this last one. So I'm going to draw in and label our curve first. And then I had a normal curve with 23 and 3. So this is 23, plus 3 would be 26, plus 3 would be 29, plus 3 would be 32. And then if I go the other way, this would be 20, minus 3 is 17, minus 3 is 14. And I might want to go ahead and just put these numbers in. So that was 34 and 34. This was 13.5%. This is 2.35%. And this is 0.15%. All right. Now, notice though that this doesn't ask for percents, it asks for proportions. So if we look at this between 20 and 26, we know that 68% of the data falls within 1 standard deviation. So 68% is what we're looking at here. As far as what proportion, though, it would be 0.68, because with proportions we write that as a decimal rather than a percent. And then when we look from 23 to 26, we're only looking at 34%, so that's 0.34. And when we look from 17 to 20, then if we're going 17 all the way to 20, then that's 2 standard deviations. Am I looking at that wrong? Oh, sorry, 17 to 20, I'm looking at that wrong. 17 to 20 would be 13.5%, so it would be 0.135, sorry, 0.135. And then above 29 would be everything above 29, so it would be the 2.35, which is written as 0.0235, plus 0.15% is 0.0015, and then that's 0.025. And then below 14 would just be the 0.0015, and below 20 would be everything below 20, so 13.5 plus 2.35, so 0.135 plus 0.0235 plus 0.0015, and that gives me 0.16. So that means that 20 is in the 16th percentile. 20 is our 16th percentile. All right, and then the last piece of this lists 3 reasons why normal distributions are important statistics. Number 1, they're good descriptions. Of real data. Number 2, they're good approximations. Of results of chance outcomes. And the one that we'll talk about probably the most is that many statistical inference procedures are based on normal distributions. So many statistical inference procedures are based on normal distributions. All right, that's it for today. Have a good day.